So now we're going to talk about something that we haven't talked about before, and this is the idea of horizontal asymptotes. Okay? So far in our discussion of rational functions, we have talked about the existence of these mysterious things called vertical asymptotes, and I gave you just a brief idea about what they're going to look like. But now we're going to talk about horizontal asymptotes. Now, when we actually graph examples, we're going to look more clearly at what horizontal and vertical asymptotes are. But for right now, I would just want to motivate this a little bit before we discuss it. Okay? And I should also say horizontal and slant asymptotes. Okay? Okay. Okay. So I want to begin with a very simple example. In fact, the most simple example of a rational function. Well, not the most simple, but one of the most simple. And it's 1 over x. Okay? And what I want you to imagine for a moment is I want you to imagine this table. Okay? And I want you to imagine, now, if we were going to graph a particular portion of the graph, let's say the 1 over x from 2 to 3, maybe we would slice 2 to 3 into a few regions, so maybe 2, 2.2, 2.4, 2.6, 2.8, and 2.3 to get some nice points so we could draw the graph very nicely. We would figure out what y's those consist of. We would figure out the x we already know. If we're graphing from 2 to 3, we would only need to plot a little bit before 2 and a little bit after 2, and we could get a very nice graph of that function, okay? But here, we want to look at the behavior as x gets very large positive or very large negative. So we already know that at 0, it's not defined. So we know that 0 is not defined, okay? Because it's not part of the domain. So we can't assign a value to that, right? But if we look very far out to the negatives, like let's say negative 100, negative 1,000, let's just leave it like that for now. And let's say 100, and maybe 10 here, and maybe negative 10 here, and then 1,000. Well, what will the f of x values be? Okay, let's look at negative 1,000. What would 1 divided by negative 1,000 be? Okay, that would be negative 0.001, right? Because we know that the third decimal place after the third decimal place is the thousandths place. So here, if I'm dividing by 1,000, that's 1,000th. So 1 over 1,000, and it's a positive. The 1 divided by the negative, so it's negative. Similarly, if I evaluate f at negative 100, I'm going to get 1 over negative 100, which will be again negative 0.00. Negative 0.01. Okay. Then here, you can see by the same reason that this will be 0.1, negative 0.1. Here, it'll be 0.1. Here, it'll be 0.01. Here, it'll be 0.001, and so on. Now, think about this for a moment. If the x continues to get larger positive, what does this look like it's going to get closer and closer to? It looks like it's going to 0, right? So if I go down toward infinity, it looks like it's going to get close to 0, right? And similarly, let me make this table a little bit up more, right? Oops. Following the same pattern, it looks like as I go this way toward negative infinity, this will go to 0. Okay? And so now what I want to imagine here is, let's imagine I'm going to draw this. I have my x-axis here. Now, as of yet, we don't know what's happening nearby here. But we can see as I'm going from 10 to 1,000, it's going towards 0 from the top. You see, because this is positive, and it's bigger than this one, but this one's also positive, so it's coming down towards 0. So let's say from 10, it's like looking like this. Something like this, right? And let's say this is like 100. This is 1,000 over here. Now, it's not bouncing up there. It's just, because I'm drawing it by hand, it's really getting smoother and smoother and smoother, closer and closer to the x-axis. And if we were to look zooming in, it's getting closer and closer forever, like this. See? Yeah, much better. Looks much better now. Now, what about if I'm going this way? By the way, we're going to graph this part in the middle later on, okay, when we're doing some real example. Well, actually, no, I'll do it right now as an example because I want you guys to see that too, and I don't want you to accuse me of like fudging this drawing just to make this point, but I think making this point is important. So look what's happening here. As I go off to negative infinity, right? Let's say negative 100, negative 1,000, okay? So by the way, you guys might also say, well, the scaling here is totally way off, and that's true here. But notice here, at negative 10, it's negative 0.1. So negative 0.1 is more negative than negative 0.01, which is, you see, the distance from the x-axis is decreasing. So let's say it's here at this point, then it's coming in like this, you see. Oops. It's not going away. It's going closer and closer, right? Getting closer and closer forever. Now, if we make a table like this, so now we know that it's undefined here. So now we're going to actually, let's take this opportunity to look at the vertical asymptote in this case. We already know that this function has a vertical asymptote at x equals 0 because, first of all, it's not defined at 0, and the x value 0 makes only the denominator 0, and we saw that that was the exact criterion for there to be a vertical asymptote. Now, if you follow a procedure like this, as we get closer to 0, okay, I'm just going to do that here real quick. Let's say, again, 0 is undefined, so, we know we're not going to get there. But let's imagine now that I'm getting close to 0. So let's say 0.001, 0.01, 0.1, negative 0.001, negative 0.01, negative 0.1, etc. Well, if I divide 1 by negative 0.001, what I'm really doing is I'm saying 1 divided by negative 1 over 1,000. When I divide by a fraction, I'm multiplying by the reciprocal, right? Okay, let me make that clear here. I'm just going to do this one calculation here. We're going to talk about these in more detail later. But anyway, I want to make this example clear so you can see what the asymptotes are. Okay, so the calculation of negative, so 1 over negative 0.001. What is that? We already know that negative 0.001 is 1 over 1,000 from what we've mentioned before. So I have a positive divided by a negative, so it'll be negative 1 over what? 1 over 1,000, right? Now what happens when we divide by a fraction? We multiply by a reciprocal, so it's going to be negative 1 times, what's the reciprocal of 1 over 1,000? 1,000 over 1. And what's that? That's going to be negative 1,000. Following the same kind of reasoning, I can see this is negative 1,000. This is negative 100. This is negative 10. This is 1,000. This is 100. This is 10. Okay, if you do this kind of procedure with all of these, you will get these values. And you can see, as I get closer to 0 from the right-hand side, the y values are shooting upwards. Okay, so in other words, here, it'll look like this. Okay, and we have to imagine that it's getting closer and closer as you get closer and closer to x. And by the same token, as I'm coming in towards 0 from the negative side, the f of x is getting increasingly negative. So it's going to look like this. Oops. Okay. And so, for example, we can say if this is, like, let's say 0.1, that would be like 10 there. And if this is negative 0.1, that would be like negative 10 there, right? Okay, so now with this example before us, I can talk about what the horizontal asymptote actually is and what the vertical asymptote actually is, okay? The x-axis here, which is another way, which is coincident with the line y equals 0, the horizontal line through y equals 0, is what the y values of the function are getting close to, both as we go off to negative infinity and as we go to positive infinity along the x, right? You can see that here in this table, and you can see it visually as the graph getting closer and closer. And so we call that our horizontal asymptote, in this case, y equals 0. The vertical asymptote is this vertical line, which is, in this case, the vertical asymptote is x equals 0. remember that the equation x equals a constant is a vertical line which goes through the constant c, and in this case x equals 0, so it's a vertical line right there going through the x equals 0, or in other words it's coincident with the y-axis, and that's our vertical asymptote in this case. And the key thing we can see about the vertical asymptote is that the function gets closer and closer to it without ever merging with it, like without ever becoming it. Okay, or yeah, same thing with this. So you can see that's why. So this is the horizontal asymptote, and that's the vertical asymptote. So now you know more closely about what they are and how they come out, and you can see where this comes from. And ironically, this is supposed to be the video on just the horizontal asymptote, but so now after we've looked at this example, now I feel confident giving you the test to find out how to find them. Okay, let's do that together. Or actually, before we go, let me just wrap this example up before we go to state the condition. Okay, look what happened here. The horizontal asymptote here is y equals 0. We can see that as x goes off to infinity, the graph of the function, of the rational function, which is this curve here, right? As I go off to infinity along the x, the function is getting closer and closer to that asymptote. Okay, and as I go toward negative infinity, the graph of the function is also getting closer and closer and closer always to that asymptote. Similarly, since this line, x equals 0, aka the y-axis, is the vertical asymptote of this function, we can also see that same kind of behavior of the graph getting closer and closer to it without ever touching it, right? Without ever touching it. It's getting closer and closer to it. That's the asymptotic behavior, okay? So let's look at this here. Okay, this is the rule. Okay. The basic fact is that if you represent your rational function r of x as this polynomial on top, a sub n of x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a1x plus a naught divided by b sub m x to the m plus b sub m minus 1 x to the n minus 1 plus dot 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 plus b1x plus b naught, then here's the different situation. If the n is bigger than m minus 1, what does that mean in plain terms? That means that the degree of the polynomial on top is more than 1 greater the degree of the bottom. So for example, if the degree of the bottom was 2, the degree of the top would have to be at least like 4. Okay, because 4 is more than 2 plus 1, which would be 3. So in the scenario that the degree of the top is greater than the degree of the bottom by more than 1, then no horizontal or slant, or also known as an oblique asymptote, will exist. Okay? Yeah. Now, the second case is if n equals to m plus 1. Like if m was 2 and the top, if the m was 2 and the n was 3, we would be in this scenario. Okay? Or if the bottom had a degree of 3 and the top had a degree of 4. Then we have a slant asymptote. And we're gonna get the slant asymptote using long division or synthetic division, depending on what the case may be, although I prefer long division. If the n equals m, what does that mean? In plain terms, that means that if the degree of the top is equal to the degree of the bottom, then the horizontal asymptote will be y equals to a sub n divided by b sub m. I'm sorry. Okay. What is that saying in plain language? That is saying that if the degree of the polynomial on top is equal to the degree of the polynomial on the bottom, then the horizontal asymptote will be the horizontal line y equals c, where the constant c is the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay? And then finally, if the, oops, yes. Finally, if the n is less than m, that is to say, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is, very simply, y equals 0. What is that? That's the horizontal line that goes through the y value 0. What is that? The x-axis. It's another name for the x-axis, okay? Okay. So now let's look at some examples. So now, We're not going to go into detail about how to calculate like how these graphs are going to look like yet in this part, but I do want to go into like some discussion of how we apply these rules with these examples before we press on forward. So the first one is we want to know what the horizontal asymptote is of this first example here. Okay. I have a 3x cubed on the top as my leading term, and I have an x on the bottom as my leading term. I want you to, so you might ask why I'm saying that, right? So whatever the case might be, you might have an example where the polynomials are not written with the degree that's highest first and with decreasing degrees afterwards. They might be all jumbled up. So you always want to look at the term with the largest degree on the top and bottom, of course, to apply these rules. Okay. In this case, so in other words, that's what I was pointing out, and I want you to keep an eye out for that. In this case, we have a cube on the top and a first power on the bottom, right? Because x is the same thing as x to the first power. Now, is the numerator power greater than m plus 1? Let's look at that. If I take the m is 1 because the power of the denominator here is 1. What's 1 plus 1? 2. Is 3 greater than 2? Yes. So what does that say? That says that this first example, this one, satisfies this first condition, and therefore it does not have a horizontal asymptote, nor does it have a slant, or also known as oblique asymptote. Okay? It has no horizontal or slant asymptote. Finito. Okay. Look at this second one here. Aha. What's the degree of the bottom of this one? It's 1, right? X is the same thing as x to the first power. What's the degree of the top one? By the way, isn't this pointer awesome? I was just noticing here as I was standing like this that I could be directing orders to be given. But instead of using my own real finger, I could be using this fake finger that makes it 10 times longer. Right? It looks more awesome. No, I'm just kidding. That's just a joke. But stick with me here. The denominator has a power of 1, a degree of 1, the polynomial. The numerator has a degree of 2. Does that satisfy the first condition? It does not. Does it satisfy the second condition? Is it the case that the degree of the numerator n is equal to the degree of the denominator m plus 1? It is. It is the case there. You can see. What's the degree of the bottom? 1. What's 1 plus 1? 2. Is that equal to the degree of the top? Yes. So we can see that it's the second case that occurs here. Okay? And so we would get the slant asymptote from this one by performing long division. Let me do that real quickly here so that you can see that and so that we can be filled with joy. Okay? So let me see here. So I would put the x minus 3 on the outside of the house, and I would put the x squared plus 5x minus 22 on the inside of the house. And so I then ask myself, how many times is x going to x squared? It goes in x times. X times x is x squared. X times minus 3 is negative 3x. Then I perform the subtraction. What is x squared minus x squared? That's gone. What is 5x minus negative 3x? Aha, that's going to be 5x plus 3x, which is going to be 8x. Then I bring down my minus 22, right? So then I ask myself the question, how many times does x go into 8x? In this case, plus 8. 8 times x is 8x. 8 times negative 3 is negative 24. What is negative 22 minus negative 24? That'll be negative 22 plus 24, which will be plus 2. Okay? So if I'm looking at this, and if you remember from our long division section, what we can see, oh my God, is that Conan? Look, it's Conan. Do you see the huge hair right here? Okay, I'm just joking. Well, yeah, it kind of looks like Conan. But anyway, I'm joking there. But so anyway, here, y equals the top, the x plus 8, and then plus the 2 divided by the x minus 3, okay? So now you might say, well, David, so this is the conclusion from this, but it's not the slant asymptote. What I want you to imagine, remember what we were talking about the asymptote. What happens as x gets extremely large positive or as x gets extremely large negative? If you look at this point, if you look at this part here, the 2 over x minus 3, if you let x get very large positive or very large negative, you can see that the 2 over x minus 3 will basically be nearly 2 over x. And as x gets huge, 2 over x goes to 0. And that's regardless of whether x is getting huge negative or huge positive. right? If I do 2 over a million minus 3, that's going to be a very small number. And it's going to be even smaller if the x is even bigger. And if the 2 is negative a million, 2 over negative a million minus 3 is negative a million and 3. 2 over that will be a very small number. And if the x gets bigger negative, it'll be even smaller still. So I'm going to be left with the y behaving like this line x plus 8 as the x goes on to infinity. So here, the slant asymptote is going to be y equals 2x plus 8. Okay? That's going to be our slant asymptote. Okay? Now, by the way, how do you call it? I'm a huge fan of Conan, so like, I don't want you to take that as in any way of denigrating Conan, but like I couldn't help noticing that it kind of looked like his hair and stuff. Yeah. No, yeah, but I'm a huge fan. Anyway, so now we look at our third example here, okay? R of x is equal to 3x squared plus 2x minus 3 divided by 2x squared minus 17x plus 14, okay? And so now we want to ask the question, what's going on with the degrees here? The degree of the polynomial on top is square, because that's the maximum power in the polynomial on the top. And the polynomial on the bottom, the maximum power is 2 as well. So they have, so I look at here, it must be this condition. If n equals m, if the power of the degree of the top equals the degree of the bottom, what does it say? Then the horizontal asymptote will be y equals an over bn, an over bm. In other words, it'll be the ratio of the leading coefficients, okay? So here, the asymptote, the horizontal asymptote, will be y equals to 3 over 2. So when I'm graphing this, I could draw that in as a dotted line, knowing that my function, as x goes to negative infinity and to positive infinity, the graph will get closer and closer to that horizontal line. Okay? Okay. Now finally we look at this example here. We see that the degree of the top polynomial is 2. We see that the degree of the bottom polynomial is 3. And we can see that, as you might have already predicted, the degree of the numerator polynomial is less than the degree of the denominator polynomial. So we are able to say that the horizontal asymptote is going to be y equals 0. In other words, another name for the x-axis. Okay. Okay. So I hope that you've enjoyed this example, and I look forward to seeing you again soon. Thank you.